Yeah, hello and welcome to the fourth session of today's Global Azure uh, Bootcamp day, whatever. Welcome to my session. My name is Markus Ehrenmueller-Jensen. The session is about hierarchies. I see a lot in business cases that there are always hierarchies, right? So you have like relations between a year and a month and a day, or you have product categories, or you have regions. So there's plenty of hierarchies out there when it comes to analytics. And this is what this talk is about. So I do a lot of I branded some of my talks with a game of hierarchies, and today I want to talk about Power BI edition. That means the problems and the solutions, how we can treat hierarchies the best in Power BI. So, if my slides here, yes. So my name is Markus Ehrenmueller-Jensen. I founded the company Savory Data. Yeah, quite active in the community, the data community Austria. There will be a full day event next year in January. So go to datacommunity.at and check out and save the date for the upcoming events. Currently also work on a book about data modeling, as I see that people are struggling with finding the right data models for their data models they want to load into Power BI. So I currently write in a book, Data Modeling with Power BI, Microsoft Power BI, and there's an early release available. So the first two chapters are already like in a row, unedited format are already available. So please check out this book if you're interested in more about this topic. But you know what Tyrion Lannister would think about a speaker slide like this? He would say, "Every fool loves to hear that is important." So this leads me also to the topic I wanted to talk about, or I want to talk about hierarchies, but I wanted also to find something which is more engaging than like product hierarchies. Something like this. So I will so in case of you wonder, if you have read the books or have seen the TV show, maybe you see people in my examples which are not alive anymore, and I see that we're getting into also I hope it's together because I'm not sure why this is. So there's no spoilers. Everything I present is like in the first book, in the first sequences of the TV show. If you're interested in the books or the TV show, I provide these links in the slides. But let's jump into the topic we're up to today. So I brought 3 episodes for this Game of Hierarchies broadcast. And one is about modeling hierarchies in general in Power BI. And then there's this special way of modeling hierarchies as a parent-child hierarchy. So if there's no limited levels available, think of an organigram like your employees. One employee reports to a manager, and the manager is just another employee in the same table. And then you would model this as a self-joined hierarchy. I will talk about this, how we can treat this in Power BI. Unfortunately, there's no straight solution. We have to transform this hierarchy, as we will learn. And if there's time at the end, I will also talk shortly about visualizing hierarchies and graphs. I talk about this shortly because usually I present hierarchies like for drill downs or in a matrix. I don't present hierarchies in the sense of like nodes are presented there. So I consider myself not too much as an expert in visualizing hierarchies, but there's some visuals we can talk about in if there's time at the end. So all the demo examples you can download from agameofhierarchies.wordpress.com. So there's a table or category of tables for points of interest. There's also, I typed in, I think it's just 1 or 2 recipes. I discovered that I get really, really hungry if I type in recipes. And there's this family tree, which we will also work today. So points of interest and family tree will be shown in demos today. Why I put in not the whole Game of Hierarchy, not the whole Game of Thrones families, but only portions of the Stark family. So how can we model hierarchies? One way of doing this is to split out things in several tables. So for example, you have a point of interest table, and then you have a name of a point of interest, and then you have another table containing the region and all the attributes, for example, the name of the region, another table for the continent, another table for the world. This is so-called normalized schema. So if you follow the rules of Edgar F. Cott and normalize your data model, which you should if you're working with application databases, which you should if you work with all so-called OLTP databases, online transaction processing databases. The normalizing is the go for because they are fully redundant free. So there's no redundancy in there because every region is only mentioned one as one row in the region. Every continent is always placed once as one row in the continent. The rows or the tables have to reference each other. So in the point of interest table, I need some way of referencing the region. So I need a region ID maybe in the region table, and I reference it from the point of interest table. So I have a foreign key in the point of interest table to the primary key of the region table in the region table. The advantage is no really, but there's a lot of disadvantages. So if you think about putting a table together where you see all the point of interest and their region and their continent and on which world they are placed, then you need to write a long statement, right? You have to query all four of those tables, and you also have to join them in the right way. Also, there's a limit in amount of groupings available because if you want to introduce a subcontinent or a super region or whatever, this means you have to change the schema. So you have to introduce a new table and point now the region to the continent and then first the subcontinent to the continent. So this makes it awkward for changes. So we have to constantly change the model if any hierarchies are introduced, for example. And in Power BI, if you think about Power BI, we can define a hierarchy, which means this is one thing in our model, which I can then take and add to my visuals, which contains several other columns. This is only possible if those several other columns are coming from the same table. So hierarchy spread out over several tables is not possible, unfortunately. So we have to group everything together into one table. So the several tables approach looks like this. I have this point of interests, I have an ID there, have the name of the point of interest, and have a region ID, which is the foreign key to my region table. The primary key in the region table is the ID column, and I also have the region name there and a continent ID, which is the foreign key to the ID column, the continent table, then you to the world. So we have four tables here for this rather simple example. We need four tables, we need four joins, we need lots of IDs and foreign keys. The other approach is to cover everything together into one single table. That means that I have just one point of interest table, and inside of this point of interest table, I already have the name of the region, the name of the continent, the name of the world. So it's not split out into four tables, but everything is in one single table. This is called a so-called denormalized schema. I don't really like the name normalizing, so I don't like the name denormalizing as well, because I think, I mean, what's normal? And yeah, it's just a term, right? The rules and making something redundancy free is a good idea. So I like the concept, but not so much the naming. And denormalizing, people could expect that if I talk about a denormalized schema, that you undo all the normalizing. And this is not what you usually do in a denormalized schema. You just flatten the dimension tables, like the point of interest. You do not flatten the fact tables if you come into that. So usually I don't name it denormalized, the term dimensional modeling, where you have dimensions and facts, and then that denormalize all the dimensions and keep the facts fully. The advantage of this is join. If I know what region a point of interest resides in, I just see it as an attribute, as a column in this row. And we still have struggles with the connection, I guess, and I'm not sure. I want to apologize for the all inconvenience here. Not sure if you can still hear me. So the advantage is also that we can use this in hierarchies when we build models for Power BI and or analysis services. So then we have to resolve those hierarchies into one single table. We have two disadvantages. One is we reintroduce redundancy because now the region name, if one region contains more than one point of interest, then the name of the region is not duplicated in this point of interest table. So I see the region twice there. So if I need to change it, I will have to make sure locations. in the data warehouse scenario, this is not a big of an issue because there's not several jobs and processes which update anything in the data model, but it's just one job which updates, for example, the point of interest table. So usually it's not too much of a challenge to make all the changes in the right way, so we don't suffer from any anomalies by changing only some region names but not the others. Still, everything is limited to a certain amount of groupings. So if I want to introduce a subcontinent, I have to change the schema. I have to introduce a new column and then use this new column in reports. But currently, there's no way around this in Power BI. So everything is in one single table, point of interest table, the name of the point of interest, the region, the continent, and the world all together. So let's see how this looks in a demo. Jump over to my demo machine. So we have here a Power BI report, a game of hierarchies, and I show the different levels I'm having here. So Azure is one of the point of interest. When I started building up this model, I called it city, but soon found out there's not so many cities, right? I'm not sure if Azure is a city. And Azure is part of the region Azure, the JDC, and the lands of the Far East. And this is then part of the continent of Essos, and everything is part of the known world. So there's no yeah, this what's there. And then just to have a measure, I just count them. So I counted this point of interest and see that like one point of interest, of course, counts for one point of interest. In Ashai, the JC, and the lens of the Far East, we have 4 points of interest. On the continent of Essos, we have 22. And of course, the known world is much bigger than 148 points of interest. But this is what I typed in to create this data model and make these things happening. So how did I create this? I need to dissolve everything. That means that in Power BI, if you take a look on the data on the tier, so this matrix contains of those things, world, continent, and so on and so forth. So this is not denormalized currently. I'm using the world name, the world table. So as we can see, there's the world table. If I thing, which looks like this, the report looks the very same. So for the report user, for the report author, for the report user, it's not difference at all. For the report author, it might be easier because everything is contained in the town table. So this current data model is like me confused by that. So I have like a town table, and this town table also contains now everything from the town hierarchy. So I have a town hierarchy here, and I gathered everything in here. So to build this report, instead of finding all the different names, different tables, with the help of this hierarchy and the denormalizer, I can drag and drop this town hierarchy element, add it to my row. So it's one thing is it's more convenient to use. The other thing is the model, if the database or the number of rows are growing, then this denormalized schema is much better and much faster, because if I take a look here to the normalized schema, so this is what you would modelize in a OLTP application database. A filter on the world means it has to be propagated first to the continent, then to the town. So we need 3 joins, not only this table, but 3 additional joins, 3 additional tables, and filters has to be propagated. So this is of course slower than having just everything in one table. So in a flattened denormalized schema, it would look like this. I just have this table and everything is in there. And I can build this in Power Query, I can build this in SQL, I can even build this in DAX. The most recommended, of course, is to build it as early as possible. So if you have a data warehouse in place, so please then manage to do everything in the data warehouse to create this in SQL. Create a view, doesn't even have to be a fully persisted table, but create a view which then contains all those joins to make it easy in Power BI. So I have one single table with all the information I need there. If I have this in the table, I can then in the view create such a hierarchy. So what I did here is I just pick, for example, you can right click here, and then you can create a hierarchy. So we see on the properties now that there's a hierarchy created for the region name, and then I can add all the other attributes I need. But very important to see that I can only select things from the same table. So if the region name or the world name or the continent name doesn't match, reside in the same table, but in other tables, I cannot select it. I cannot build a hierarchy in here. So that's about the hierarchies. If there's any question, please make sure through your comments, so I can react to any questions if there are some. Jumping back to the slides. So denormalizing, very, very important for dimensional modeling. And Power BI, and also to point out, make sure this, so the dimensional modeling, the denormalized model is not superior per se over the normalized or a one big table. I also see people using one big table. This is very useful in Excel, for example, to put everything, not only the continent and the point of interest, but all the measures like the counts or the revenue or whatever in one single broad table. Some people call this OBT. Sounds really fancy, right? It's one big table, everything there. And it's also a valid approach if you think, depending on what kind of tools you're using. So in Excel, the one big table approach is superior because that's the best. Everything there, then you use this as a basis for your pivot table and start doing your analytics. In an application database, this would not be good because you have all this redundancy and all the things that could happen if there's some mistake in your code and then only certain region names are updated, but the others are still the old name, and then you end up when you group up you do your queries, you end up with groupings like having two different regions, still one region in the reality, but it's different regions shown in the report then. So this is bad. That's why you do the third normal form there. But for analytics in Power BI, there's something in between which is the best for Power BI, which is the denormalized model, the dimensional model, where you're not having everything in one big table, where we're not having everything split out, but built as a dimensional model, which means you have to find out what's your fact tables, what's your dimension tables, and then you denormalize all your dimension tables. And when you do that, then you end up with the approach I just have shown you, to have one point of interest table, all the attributes there, and then you can easily build your model on that and your hierarchies. A little bit more tricky, but much more interesting are the parent-child hierarchies. So parent-child hierarchy is usually modeled in a relational database as a self-joining table. That means that I have a family table, for example, and this family has a pre-key for an ID, and then every member reference who is her or his father. You can also build this with the mother side, of course. But the father ID, that's the important thing, is not a foreign key to another table, but it's a foreign key to another row in the same table. So the father ID is a foreign key on the ID of the same table. So the reference, a foreign key is always referencing a different row, but usually a different table. In the in the case of self-joining tables, this means that it's referencing another row in the same table. The advantage with this is again redundancy free. So every member is only mentioned one ID, and several other family members can reference this member as their father. You can also have an unlimited amount of levels, because if there's a newborn, right, you just add another row in this table. This new child gets an own ID on its own and then referencing his or her father. And this can be endless, right? There's an unlimited amount of levels possible. The disadvantage is we need joins again. So everything is not in place in one table, but we need to join between one row of this table to the other row and to the other row and other row. So because if you want to dissolve the full hierarchy, you have to go through all those unlimited amount of levels, right? If you want to write this in SQL or T-SQL, so in SQL you can use common table expressions, recursive common table expressions to resolve this, so you're not limiting yourself on the amount of levels you're querying. Or you could write in T-SQL a loop. You could write like start with one element there and loop and loop over this hierarchies, and also dissolve the self-joining table. Unfortunately, Power BI cannot handle such tables on its own directly, so we again have to dissolve it and form the self-joining table, or transform this self-joining table into a format we previously have seen. Like we need one column per level. So all the advantages of unlimited level, unfortunately, is gone when we think about Power BI. So when we dissolve this, you should have some extra levels prepared in case of new levels are added to the data model, that your Power BI report still shows all those levels. So the self-joined table looks like this. We have this family table and this other ID on the ID column of the same table. And in an ERD diagram, you would see it like something like this. You get this ear, like there's a relationship going from this table back to the table again. The intermediate step to gain this in Power BI is to transform this self-referencing hierarchy into a materialized path. So what is a materialized path? Materialized path means that I come up with a string which contains all like the node, the number of the node of the node itself, but also shows what are all the ascendants. So like the father, the grandfather, and so on and so forth. This is stored in one single string, in one single column. Therefore, we don't need any filter relationships, because from this column, from this attribute, I can derive who is the father, who is the grandfather, and so on, or the other way around. And it would look like this. So, for example, if you use a materials path for our IDs, like the grandfather, in our case, it will be Ben, top this hierarchy of the top of the family tree, and then I build a materials path. So this means for node 102, obviously 102 is a descendant of 100, as we can see graphically in this diagram, but we can also see from the node materials path. So the path for this node 102 contains not only 102, but also 100 and a separator in there. We need a separator because otherwise we cannot distinguish like 100102 and 10102, right? So we need some separator in there. And this approach is valid for all the nodes. So when I look at this node's number is 105. Obviously, 105 is a descendant of 104, and 104 is a descendant of 102, and 102 is the descendant of 100. So just by knowing this materials path, I know where a node resides inside of a hierarchy. Not a network, but a hierarchy. And we can build this in DAX. So either we can build this in DAX, we can build this in SQL, or we can build this in Power Query. Let's see how much time is left, 50 minutes. So let's speed up so we can see plenty of code here for the rest of this talk. So the materials path means that, no, it's 20 minutes to go, right? 45. The materials path is that, fortunately, there is a function available in DAX, which is called path. And for the path, I pass in the ID, the primary key of my table, and the foreign key of the table. Exactly the columns we just have talked about, right? The ID is the primary key. The father ID is a reference to the ID of another row in the same table. By calling this path function, exactly these strings are built up for me in DAX. So I don't have to think about too much. The next thing you should do then is to derive what's the first level, because we have the materials path alone is not enough, but we need to put like the name of the CEO. Let's go back to the organigrams. Like this, the name of the CEO must be shown in all rows in the column level 1 or CEO level or whatever. So for every row, I build then this table at this column level 1, and level 1 is using this the path, right? So the path is exactly this one. So I build a column in my data model called path, and it contains this expression. And then I reference this other column in my level 1 calculation, where I calculate, please return me from this path the first element. And O1 is an integer. No, not O1 is an integer, but what I get back, like the ID is an integer. This is what I'm asking here for. So level key will be an integer. And what I want is return me the top element of this path. So this would be, in this case, there's only one element, right? It's 100. In this case, it's also 100 because the top level is 100. And then I built this, and then I look up whatever I get back. So I get 100 back, and I use a lookup function where I ask DAX, please return me the first name, for example, Ben, or the name of the CEO. And I want to identify this first name by passing in the ID. So I'm looking, please compare look up for the ID there, and compare it with this level key. So get returned 100, looks up the row in the family table where ID is 100, and then returns the first name. And this is what I would store in level 01. Of course, and then add another column, level 02, level 03, and so forth. And the only thing you have to change is always this number here. That's why I put this in bold font. So we created plenty of columns. Whatever you think of is the maximum number of levels, and then maybe add still some more. So create lots of these levels, these columns per level. And then we can create a hierarchy on that. So I create a hierarchy where I put level 1, level 2, and so on in this hierarchy, and then the users can just use it. Optionally, sometimes this can be useful. I want to know if some family member is a leaf level or not. And in IT, leaf level is a little bit confusing because if you think of a tree, right, then you have the branches, right? And top of the branches, you have the leaves. But in IT, it's always the other way around. So if you think about leaves, it's the lowest levels, those nodes which don't have any children anymore. So back in our tree, and this is a tree, right? But the tree is turned upside down. So these are the leaf levels, and those are branches and not leaf levels. So leaf level is something which doesn't have any child. This is what we can check here. So I can check if the family ID of the current row can be found as a father ID. If it can be found as a father ID, then the current node is not a leaf level. It's somewhere in between in this hierarchy, and is mentioned as a father. So if it can be found, then we return not a leaf, and if it cannot be found, obviously it's a leaf. So let's see how we can build this in DAX. To our table, maybe I jump over here. And this. So the basis of this table looks like this. I have my most important column D here. I have my ID long, shortcut, this one. Both them I for ID. So Recon is the son of father ID 100. Recon is the son of Bench. By at Recon, the father is 100. Recon himself is also a father. He's the father of Gregan, as we can see here. Gregan mentions 102, and 102 is mentioned here, and so forth. And this is how this tree is built up as a self-referencing join. But what we need is, I need a column which tells me that level 1 is pension for all of my rows who are descendants of pensions. And this is what we get at the very right here. Let's jump over here and zoom in here. Path, right? So we're talking path. It's just 100, right? For Recon, it's 102, 1,400. So with this path, I know on which level a node resides and who are the ascendants. And the next thing what we then did was that I built this level thing where I then look what's the name, the first name of the first element. And for pension, there's only one element, so it himself. Recon is also a descendant of pension, so pension 100 is the first element in my first cell. For example, for Lysa, for example, it's something different. So there's a different path in there, different hierarchies in there, because there's different the longer the hierarchy gets, right, the more descendants you have for a node. If there is no level 2 available, it will not be found. Right? If it's 100, it will not return anything, so there's no level 02 available for pension, which is okay because he's on top of the list. The levels are here, right? So the path, again, let's take a look on the path. The path is here. Just this simple expression. Why I ask, please create a calculated column path and call path empty. Seen on the slides. And for this level 1, level 2, there's like as a parameter in here, and that's the same expression we just have seen in the slides. And for the other levels, it's the same expression but different numbers, right? So the only thing I had to change is not to change anything inside of my query, just change and make sure that it uses a variable here in Dux is just the same. If we build a report with this, that's what we see here, the family materialized, all the different levels. So maybe we're the solution for your problem, but maybe you need to report the report more like this, where we need like different elements of this hierarchy, and then I want to expand and collapse things, right? I want to know pension. Number of children of pension is 13 in this model. And if I then expand it, I would like to see only recon, right? I don't want to see those empty values. I want to see recon and then expand recon and then see the sick recon, whoever is then in this model. So the problem we're facing here is that, of course, what I'm showing here is level 1, level 2, level 3, and so on and so forth. And those levels are available, but what I want to avoid is that those levels should not be shown. So the trick here is the following, that calculate, one hand, what is the maximum path length for a certain element, and what's the current element I'm showing in my report. So I don't want to show this row, the current two, but for pension, there is nothing available on level 2, right? Because pension is on the top level in my hierarchy. So this is what is the next challenge, to calculate those things. So the min path length, we take a look here. The min path length is the minimum path length. So what's the path length? The path length is a path. I also have a function path length available. I pass in the path, and it will return me what's the level. So for pension, 100, there's nothing else in the path, right? So this is on level 1. For recon, it's on level 2 because the path tells me 100, pipe sample 102. So there's one pipe sample and 2 levels. So this will return 2. So this is what this does. And the minimum per not employee, of course, but per family member. The current level on the screen or in the visual is something different, like a long statement, but does the following trick. So what it does is in scope is checking if something, for example, the level 1 is in the scope of the current visual. That means here level 1 is in scope, right? Because I'm showing pension. Pension is the content of level 1. Here, level 2 is in scope. Here, level 3 is in scope. But if level 3 is in scope, of course, also level 2 and level 1 is in scope. Think of a scope like a filter. So for this row here, there's a filter not only on this level 3, but also on level 2, because level 3 is part of level 2, right? And also on level 2. So for this element here, level 1, level 2, and level 3 is in scope. And this is what I'm checking here. So I check if some level is in scope, and this function returns me true or false. So if level 1 is in scope, like for pension, it is in scope, so it returns true. On the next element here, level 1 is also in scope. But here at level pension, level 2 is not in scope, so this is returning false. And by default, also DAX can convert by Boolean numbers, true and false, to numerics, right? So if it's if this is true, and another check if something isn't true, because this will be converted, true will be converted to 1, and false will be converted to 0. So if only level 1 is in scope, like level, at this line, only pension is in scope. You can see this is returning only 1 because at level 9 and so on is not in scope. So this all are returning 0. Only this one returns 1. This is why we get 1 returned. On the next level here, as I told you, this is level 2, but when level 2 is in scope, also level 1 is in scope. So these functions, the first one and the second one return true plus true. 1 plus 1 is 2. The rest is 0, so 2 is returned. Only return something in my measure when this min path length is lower equal than the current level. This, what's the goal is that if I expand pension or collapse pension, I don't want this. So anytime you have these ragged hierarchies, you need to handle those which level is the node on the which level I'm currently presenting here. So so number of children. The first thing is here I count the rows. So how many rows are available for this member, right? This is the number of children, number of descendants. But then I check here that the current level must be lower or equal than 2 and right? So if I add them back again, so this was this current level and the level is exactly what we have used or I have used here in this number of children. So I'm checking if this lower equal than the other one. If this is the case, I return the value. In all the other cases, I don't return anything. So this I can prevent with racket hierarchies that I get this empty elements. So if you're facing these empty elements, it's because you need to see the slides. So this is what also is described here. So for the racket hierarchies, we have to know on which level something is. The path length returns this. And finding the current level within the visual is a measure. This is not a column, but a measure, checking if some level is in scope or not. So I'm knowing at which level currently is presented. And in my measure, I'm making sure that this minimum of the path length is always bigger or equal to the current level I'm showing. So I'm not showing something when there's no information available. Just did this. In Power Query, the story is similar. There's no direct function to come up with the materials path, but we can use the user interface to build the same elements. So if you prefer not doing this in DAX, but in Power Query, of course, we can also do that. And that's the cool thing with Power Query, you can write functions. So in DAX, we have to think about how many levels do we return, right? So we can build this extra columns, level 1, level 2, and so on. In Power Query, we can do the same thing, but there's also the possibility that we write a function. So the function does this thing for us. And go to the Power Query editor where we transform data, open this Power Query window, and family tree. So what I did here is the store step here, all my not employees but family members, and then I merge queries here. So the easy way is like to think, okay, I need to know what the father of Recon is. The father of Recon is like the node where the father ID equals the ID. So I merge the queries, ask for merging this query into the step here. I will not do this, just demonstrate here. And I ask them, please, for my for Recon, I need the father ID, right? And then I find the father ID in the same table. So I have the family, let's take the same one, the family flattened, the current one. So I'm merging my family flattened table with the same table, but look up, not the father level, this is wrong, the father ID as the ID. So what I then get, I join this table. So I now have like all the elements, like for, what do we have here? 100, like for 102 Recon, his father is 100. So I join this row pension with all the attributes I've mentioned to this row, and then I can make use and refer to level 1. And this is what I did here for all my levels, right? So I merged this, add only like the first name and the father ID, because I then have to use this father ID to the next merge and so on and so forth. So as I expect 10 levels, I did this for 10 levels. Then added the path in here, concatenate then everything again as the path to get this materials path, this element here. I added a column for the path length, which is just I'm counting how many pipe samples, pipe characters I'm having, plus 1, right? Because like this is on level 2. You can look here, zoom in here. So this would be on level 2. It's on level 2 because there's one pipe, so I add 1, right? Or this one would be on level 3, 1, 2, 3 levels. It's 2 pipes plus 1 is level 3. And then I also checked if something is a leaf level. So I'm again looking at D as a father ID somewhere in my. And with it, I have to introduce Hierarchies here, which is like awkward to define. And also I have to go here and add those levels. So what I found is, unfortunately, not myself, but what I found is that Imke Feldman. So if you do anything about Power Query, then the BI accountant is the go forward. And she does tremendous things in Power Query. So what she came up with, those elements, introducing those elements, introducing the path length, splitting everything into several columns, having the path level in there. So by just calling this function, I get this result. This is what I did here. So instead of having all those steps here, I just call it in my source step here. I'm calling this function. So this is the function of Imke Feldman. And I just call this function and query family and the column names. So what's the ID, what's the primary key, what's the foreign key, and what do I want to return for the levels. And this function will then take care of everything. So I have my path in here, I have the level 1, level 2 already dissolved. So this is like more pain-free. Of course, if levels are added, I have to come here and to refresh everything, and then also like maybe change my reports to add those levels. But all those manual steps in dissolving the hierarchy via joins with merge in Power Query, this is something you can get rid of. And then you get the same experience. You still need, of course, to take care of this. So even for this family flattened, for example, I have my mean path length and number of children in there. So I handle the racket hierarchies. So if you use self-contained, self-joining hierarchies in Power BI, you can produce the materials path and all those columns either in DAX or in Power Query. But to cover the racket hierarchies, you need to write some DAX. And of course, you can do this very same also in SQL. Unfortunately, I'm running out of time.